And we're back. First, we find r prime. The derivative of sine of t would be cosine of t. The derivative of cosine of t is negative sine of t. And then the derivative of t is 1. Next, we find the magnitude of that. So we would have the square root of cosine squared t plus negative sine t squared plus 1 squared. If we square the negative sine of t, that would give us a positive sine squared t. So then we have cosine squared t plus sine squared t combined would be 1. And then 1 plus 1 is equal to 2. So we have radical 2. We have the integral from 0 to 2 pi of radical 2 dt. This would give us radical 2 times t from 0 to 2 pi. So then we get radical 2 times 2 pi minus 0. And then that would be 2 pi root 2. For example 4, we have to find the length of the helix. Notice that inside of this helix, there's a variable a. That a means that we will not be able to use the calculator or Desmos to evaluate this integral. We're forced to do this by hand. Pause the video and see if you can figure out how to solve. This would also be an interesting one to graph inside of GeoGebra to see what the curve looks like. And we're back. First up, we want to find r prime. First, we have to take the derivative of sine of t. That would be cosine of t. Then we take the derivative of cosine of t. That is negative sine of t. And then the derivative of a of t. And then the derivative of a of t would just be a. If we find the magnitude of that, we then have the square root of cosine squared t plus sine squared t plus a squared. Cosine squared t plus sine squared t is equal to 1. So this would give us the square root of 1 plus a squared. Keep in mind that a is just some constant. A is not a variable. We then can use the arc length formula. We have the integral from 0 to n pi. N is also a constant. It's not a variable. We have the radical of 1 plus a squared dt. The antiderivative of this would be square root of 1 plus a squared times the variable t, and the interval goes from 0 to n pi. That would give us the square root of 1 plus a squared. Plugging in the boundaries for t would give us n pi minus 0. So then our answer here is n pi, square root of 1 plus a squared. The second part of this question says to use the result to find the value of a that will create an arc length of 60 using 3 turns of the helix. So this part is where looking at the graph of the helix might help. GeoGebra automatically created these boundaries for t. The boundaries it created were 0 to 2 pi. But in the problem, we have this value of n, which means that the upper boundary could be anything. Instead of 2 pi, I'm just going to make this 12 pi, just so we can see what happens for a higher upper boundary. So this is what the helix looks like with an upper boundary of 12 pi. And now if we move the slider for a, we can see that we have a longer helix. So the question we're trying to answer is what value of a will create an arc length of 60 using 3 turns of the helix. So the first step is to figure out what value of n would give us exactly 3 turns of the helix. Right now we have 1, 2, 3, 4, 5, 6. We have about 6 turns of the helix. How many turns of the helix has to do with our upper boundary, n pi. If we flatten this out, we can see that the radius of the circle is just 1. That circle is created from sine of t, cosine of t, in the x and y components of the vector value function. A radius of 1 means that we could compare this to the unit circle. and 1 revolution around the unit circle is 2 pi. If we want to make 3 revolutions of the helix, that means that we could compare that to 3 revolutions of the unit circle. So 3 times 2 pi would be 6 pi. Let's change the upper boundary from 12 pi to 6 pi and see if that gives us 3 revolutions. And it does. We can see from this picture that this helix is going around exactly 3 times. We want our upper boundary to be equal to 6 pi, and our upper boundary here is defined by n pi. That means our specific value of n we need is 6. The arc length formula we found earlier was n pi square root of 1 plus a squared. The problem says that we want this arc length to be equal to 60. Substitute our value of n is equal to 6, and then we can solve for a. So we have 6 pi square root of 1 plus a squared is equal to 60. Divide both sides by 6 pi. That gives us the square root of 1 plus a squared is equal to 10 over pi. We can square both sides. 1 plus a squared is equal to 100 over pi squared. Finally, we can subtract 1 from both sides and then take the square root. That'll give us a is equal to the square root of 100 over pi squared minus, and then in the calculator I find that this answer is 3.022.